Have you ever looked up at the night sky and felt that sense of awe, that humbling reminder of how vast and mysterious the universe truly is? Among the countless wonders scattered across the cosmos, few captivate our imagination like black holes. These enigmatic cosmic monsters don't just swallow light, they warp the very fabric of reality, challenging everything we think we know about space and time. Today, we're diving deep into the heart of these gravitational beasts to uncover 30 astonishing black hole facts that will completely shift how you see the universe. Imagine a place where gravity is so overwhelming that not even light can escape its pull, a region where the laws of physics as we know them begin to break down. Black holes aren't just science fiction, they're real, they're powerful, and they hold secrets about the birth and death of stars, the structure of galaxies, and perhaps even the ultimate fate of our cosmos. From stellar mass black holes formed from collapsing stars to supermassive giants lurking at the centers of galaxies, each one tells a story of cosmic violence and beauty. This journey isn't just about facts and figures, it's about expanding your perspective, awakening your curiosity, and connecting you to the grand tapestry of the universe. We'll explore how black holes distort time, create unimaginable densities, and even influence the formation of new stars and planets. Whether you're a seasoned space enthusiast or just beginning to explore the mysteries above, these insights will leave you with a deeper appreciation for the strange and magnificent forces shaping our reality. So settle in, open your mind, and get ready to see the cosmos in a whole new light. Let's start with a fact that might reshape your entire understanding right from the beginning. The term black hole itself is a bit of a cosmic misnomer. We often picture them as empty voids, like a dark pit in space, but that couldn't be further from the truth. In reality, a black hole is an incredibly dense, compact object packing an almost unimaginable amount of matter into an astoundingly small space. Think of it like this: our sun is a massive sphere of hot plasma over 860,000 miles wide. Now, imagine crushing all of that mass, all of that material, down into a sphere just a few miles across. The density would become so extreme that the force of gravity it generates would be utterly overwhelming. This is essentially what happens at the end of a very massive star's life. When such a star runs out of its nuclear fuel, it can no longer support its own immense weight against the crush of gravity. Its core collapses catastrophically in on itself in a supernova explosion, and if the remaining core is massive enough, nothing can stop the collapse. It just keeps compressing until it forms a black hole. So why do we call it a hole if it's a physical object? The name comes from the effect it has on space-time. The gravitational pull is so powerful that there is a boundary around it called the event horizon. This isn't a physical surface you could touch, it's more like a point of no return. Once anything, including light, crosses that invisible threshold, it can never escape. From our perspective outside, the region inside the event horizon appears completely black, a hole from which nothing returns. This gives the illusion of an empty, dark abyss, when in fact it contains an extraordinary concentration of matter. A common analogy is to call them cosmic vacuum cleaners, endlessly sucking in everything around them. But this isn't entirely accurate either. A black hole's gravity works just like the gravity of any other object, such as a star or a planet. If our sun were suddenly replaced by a black hole of exactly the same mass, Earth and all the other planets would continue to orbit it perfectly normally. They wouldn't be instantly sucked in. The terrifying pull we associate with black holes only becomes inescapable once you venture extremely close past that event horizon. They are less like voracious vacuum cleaners and more like the most profound gravitational traps in the universe, warping space around them so intensely that they create a one-way door into a realm of ultimate density. Building on that idea of a gravitational trap, the event horizon is the ultimate point of no return. This invisible boundary is the defining feature of a black hole, the moment where the universe's rules as we know them cease to apply. While it's often depicted as a fiery, swirling ring, the event horizon itself has no physical substance. You couldn't touch it or land on it. It's a mathematical boundary in space, a threshold where the black hole's gravitational pull becomes so intense that the escape velocity, the speed needed to break free, exceeds the speed of light. Since nothing in our universe can travel faster than light, crossing this line means there is absolutely no way to reverse course. It's a one-way door slammed shut by the laws of physics. To understand what happens to an object daring enough to cross that threshold, we have to consider the brutal force of gravity. Gravity isn't a uniform force, it's stronger the closer you are to the source. This difference in pull, known as a tidal force, is what causes the ocean tides on Earth from the Moon's gravity. Near a black hole, this effect is magnified to an almost unimaginable extreme. As an object approaches the event horizon, the part of it that is closer to the black hole feels a significantly stronger gravitational pull than the part farther away. This difference stretches the object lengthwise while simultaneously compressing it from the sides. The result is a grotesque and violent process scientists call spaghettification. A person or a star would be stretched out into a long, thin stream of particles, like a piece of cosmic spaghetti, before being pulled into the singularity at the center. Perhaps the most profound consequence of crossing the event horizon is the complete and permanent severing of communication. According to our current understanding of physics, not even information can escape. Any signal, a beam of light, a radio wave, a desperate message sent from inside the event horizon can never reach the outside universe. This creates what physicists call an information paradox, a major puzzle about what truly happens to all the information about the matter that falls in. Does it get destroyed, which would violate a fundamental principle of quantum mechanics, or is it somehow preserved? This question remains one of the biggest unsolved mysteries in theoretical physics, pitting the laws of general relativity against those of quantum mechanics in a battle for the ultimate truth about our reality. The event horizon, therefore, isn't just a boundary in space, it's a curtain drawn across the universe, forever hiding the secrets within. While the event horizon marks the boundary of a black hole's influence, these cosmic objects are not all created equal. In fact, the black holes we've been describing so far are the relatively small ones, born from the death of massive stars. But there is another, far more colossal class of black hole that commands an entire galaxy. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These are not mere stellar remnants, they are cosmic behemoths containing millions or even billions of times the mass of our Sun, and their gravitational dominance shapes the destiny of their entire galactic homes. Our own galactic center is a perfect example. 26,000 light-years away, in the constellation Sagittarius, lies a faint but incredibly powerful radio source known as Sagittarius A. For decades, astronomers suspected this was the location of a supermassive black hole, but it was the patient tracking of stars orbiting this invisible point that provided the undeniable proof. Scientists observed a group of stars whipping around an empty spot at speeds exceeding 3 million miles per hour. The only object with enough gravity to hold these stars in such a frenzied, tight orbit is a supermassive black hole. We now know Sagittarius A has a mass equivalent to about 4 million suns, all compressed into a region of space no larger than our solar system. It sits there, a silent and dark monarch, presiding over the vast whirl of stars, gas, and dust that makes up the Milky Way. The existence of these giants raises a profound question: how do they get so big? Their formation is one of the great puzzles in astrophysics. They did not form from a single collapsing star. That process could never create such immense objects. One leading theory suggests they started as smaller seed black holes in the early, dense universe, merging with others and voraciously consuming vast amounts of surrounding gas to grow to their staggering sizes over billions of years. Another fascinating idea is that they could have formed directly from the collapse of enormous clouds of primordial gas, skipping the star stage entirely. However they began, their growth is intrinsically linked to the evolution of their host galaxy. This relationship is a cosmic dance of creation and destruction. The supermassive black hole's immense gravity funnels gas and dust toward it, heating this material to incredible temperatures and causing it to shine brilliantly as it swirls in an accretion disk before falling in. This process can create an active galactic nucleus, one of the most energetic phenomena in the universe, shining brighter than all the stars in the galaxy combined. But this feast also has a profound feedback effect. The tremendous energy released by the black hole, in the form of radiation and powerful jets of particles, can actually blow surrounding gas away. This might sound destructive, and it can be, but it also serves a regulatory purpose. By heating and dispersing the raw material for new stars, the black hole can effectively put a limit on its own growth and quench star formation in the central regions of the galaxy. In this way, the supermassive black hole acts as a gravitational heart for the galaxy, its powerful beats influencing the birth of stars and the very structure of the cosmic island it calls home. Now, just as a star's collapse can create a black hole with immense gravity, the same process can also set it spinning at a truly mind-bending rate. Many black holes are not just sitting passively in space, they are rotating, some at velocities approaching the speed of light itself. This spin isn't like a planet rotating on its axis, it's a fundamental property that twists the very fabric of the universe around it. When a massive star collapses to form a black hole, it holds onto its original angular momentum, the same property that causes a figure skater to spin faster as they pull their arms in. Imagine that star, which might have been rotating slowly over millions of years, suddenly having all of its mass crushed into an infinitely tiny point. To conserve that momentum, the resulting black hole must spin at an incredible velocity. We're talking about rotations that can complete a full revolution in just a fraction of a second. This creates a vortex of spacetime so powerful that it literally drags the universe along with it. This phenomenon is known as frame dragging, a prediction of Einstein's general relativity. Picture the fabric of spacetime as a vast, still sheet. A non-spinning black hole would be like a heavy bowling ball creating a deep, stationary dent in that sheet. But a spinning black hole is like that same bowling ball now spinning rapidly within the sheet, twisting the fabric around it into a swirling whirlpool. Anything that comes near light, dust, even entire stars is forced to move with this current. The black hole's rotation doesn't just affect objects within its event horizon. It warps the entire region of space surrounding it, creating an ergosphere where it becomes impossible to stand still. You would be compelled to move in the direction of the spin, caught in the cosmic current of a gravitational maelstrom. So how do we, from thousands or millions of light years away, possibly measure the spin of an invisible object? Astronomers have developed incredibly clever methods, often relying on the black hole's relationship with its immediate environment. Many black holes are surrounded by an accretion disk, a superheated, glowing whirlpool of gas and dust spiraling inward. The inner edge of this disk is dictated by the black hole's spin. A non-spinning black hole has a larger, more distant inner edge, but a rapidly spinning black hole drags spacetime around it so forcefully that it pulls the inner edge of the disk much closer to the event horizon. Material in this tighter orbit is heated to even more extreme temperatures and moves at a significant fraction of light speed, emitting intense and specific high-energy X-rays. By analyzing the spectrum of these X-rays with space telescopes, scientists can detect subtle distortions. A telltale smearing or broadening of specific ion emission lines in the X-ray light reveals the ferocious speed of the orbiting material, which in turn acts as a direct proxy for measuring the black hole's spin itself. It's a cosmic fingerprint, a unique signature left in the light by the relentless, dizzying spin of gravity's ultimate engine. This mind-bending distortion of space around a spinning black hole is just one incredible consequence of Einstein's theory of general relativity. But perhaps the most profoundly strange effect of such intense gravity is what it does to time itself. According to Einstein's predictions, time is not the universal constant we experience in our daily lives. It's malleable, and it can be stretched and warped by gravity. Nowhere is this effect more extreme than in the vicinity of a black hole, where gravity reaches its absolute peak. Let's use a thought experiment to make sense of this, a scenario often called the twin paradox. Imagine two brave astronauts. One, let's call them Alex, stays on a spaceship a safe distance away from a black hole. The other, Sam, volunteers to pilot a small probe on a mission to fly very close to the event horizon, taking measurements before returning. From Alex's perspective on the ship, watching through a powerful telescope, something peculiar happens as Sam approaches the black hole. The light coming from Sam's probe begins to slow down, stretching into longer, redder wavelengths in a process called gravitational redshift. But more astonishingly, Alex sees Sam's movements becoming slower and slower. A simple wave of the hand appears to take minutes, then hours. Sam's entire probe seems to be moving in an agonizingly slow, surreal slow motion. But what is the experience like for Sam inside the probe? From their perspective, everything is perfectly normal. Their clock ticks at its usual rate, their heart beats normally, and they complete their scientific checks in what feels like a standard amount of time. After what feels like just a few hours of work near the black hole, Sam turns the probe around and heads back to the ship. Upon reuniting with Alex, Sam is in for the shock of their life. For Alex, decades have passed. Their fellow astronaut has aged years, while Sam has aged only hours. A mission that felt like an afternoon for the traveler was a lifetime of waiting for the one who stayed behind. This isn't just science fiction, it's a direct prediction of Einstein's physics known as gravitational time dilation. Gravity doesn't just pull on matter, it pulls on time, slowing its passage. The stronger the gravitational field, the more time slows down relative to a weaker field. Near a black hole where gravity is almost infinitely strong, this effect becomes astronomical. A single minute for someone hovering just outside the event horizon could equate to years, centuries, or even millennia passing for observers in the distant universe. This demonstrates a core principle of relativity. There is no single, universal now. The passage of time is a personal experience, deeply dependent on your local environment and your motion through space-time. This has staggering implications for how we understand the universe. If we could observe a star collapsing into a black hole from a safe distance, the final moments of its collapse would appear to us to take forever. From our perspective, the star would seem to freeze at the point of forming its event horizon, fading from view over an immense timescale due to the extreme redshift. For the material of the star itself, from its own reference frame, it would cross the event horizon and reach the singularity in a finite and probably very brief amount of time. Two completely different realities, both true from their own perspectives. This phenomenon forces us to abandon the idea of a single, objective timeline for the cosmos and accept that time itself is a fluid, relative dimension, woven inseparably with the fabric of space and bent into strange new shapes by the awesome power of gravity. For all their terrifying power and inescapable gravity, the idea that black holes might one day vanish entirely seems to defy their very nature. Yet this is precisely the startling conclusion of one of the most brilliant minds in modern physics. Stephen Hawking proposed a revolutionary theory that merged the vast scales of general relativity with the bizarre, probabilistic world of quantum mechanics. And in doing so, he revealed that black holes are not the eternal prisons we once thought. They have a lifespan and they can, in fact, fade away. This process hinges on a strange quantum phenomenon that occurs right at the very edge of the event horizon. In the seemingly empty vacuum of space, pairs of virtual particles are constantly flickering in and out of existence. These are not true particles in the usual sense. They are quantum fluctuations, borrowing energy from the vacuum for an impossibly brief moment before they inevitably collide and annihilate each other, returning the energy and vanishing without a trace. This is happening everywhere all the time, and normally the effect cancels itself out completely. But place this quantum activity at the precipice of a black hole and everything changes. Hawking realized that if one of these particle pairs pops into existence right at the event horizon, the immense gravitational pull can tear them apart before they have a chance to annihilate. In this cosmic robbery, one particle falls across the threshold, forever lost to the black hole, while its partner is ejected out into space, escaping as real radiation. This is Hawking radiation. From the perspective of a distant observer, it appears as if the black hole itself is glowing, emitting a faint whisper of particles and energy. But this emission comes at a direct cost. To preserve the fundamental laws of energy conservation, the particle that fell in must have had negative energy. This means the black hole doesn't just lose the mass equivalent of the escaped particle. It actually loses slightly more mass than it gained. With every pair of particles separated, the black hole's mass shrinks by a tiny, almost immeasurable amount. For a stellar mass or supermassive black hole, this process is incredibly slow, taking far longer than the current age of the universe to have any noticeable effect. A black hole with the mass of our Sun would take an almost inconceivable number of years to evaporate, a 1 followed by 67 zeros. But for a much smaller, primordial black hole, theorized to have formed in the intense density of the early universe, the story could be very different. A black hole with the mass of a small asteroid would be emitting Hawking radiation at a tremendous rate, heating up as it shrinks and finally ending its life in a spectacular flash of gamma rays, a final burst of energy signaling its complete evaporation. Hawking's discovery fundamentally changed our understanding of black holes. They are no longer seen as eternal, static in points, but as dynamic objects with a temperature and a life cycle. This also created a profound paradox. The information about all the matter that ever fell into the black hole, what it was made of, its structure, its history, seemed to be lost forever when the black hole evaporates, violating a cornerstone of quantum mechanics which states that information cannot be destroyed. The resolution of this black hole information paradox remains one of the most active and heated debates in theoretical physics, a lasting testament to how Hawking's elegant idea opened a doorway to deeper mysteries about the fundamental nature of our reality. While the slow evaporation of a black hole is a quiet, theoretical process playing out over eons, their most dramatic and energetic moments come from violent collisions. Black holes are not always solitary hunters. They can exist in pairs, locked in a gravitational embrace, and when they finally spiral together and merge, they unleash a storm of energy so powerful that it literally shakes the fabric of the cosmos. We've moved from the faint whisper of Hawking radiation to the universe-shattering crash of a black hole merger. This incredible dance begins when two black holes orbit each other, forming a binary system. They might be the remnants of two massive stars that were born together as a binary pair and lived and died together, or they could be two lone black holes that found each other later, drawn together by their immense gravity within a dense star cluster. As they circle one another, they lose energy in a very subtle but relentless way by emitting gravitational waves. Predicted by Einstein, these are not waves of light or sound, but literal ripples in the fabric of space-time itself. Imagine the universe as a taut rubber sheet. When massive objects like black holes orbit each other, their motion creates waves that radiate outward, much like ripples spreading across the surface of a pond after a stone is dropped. For most of their cosmic dance, this energy loss is minimal. But as the black holes get closer and their orbital speeds increase, the emission of gravitational waves becomes tremendously powerful. They begin to spiral inward faster and faster in a tightening, fatal orbit. In the final moments before a merger, they can be whipping around each other at a significant fraction of the speed of light. This is when the most incredible energy release occurs, when they finally collide and become one. An amount of energy equivalent to several times the mass of our Sun is converted into gravitational waves and blasted across the universe in a fraction of a second. To put that cataclysmic power into perspective, the peak energy output of a black hole merger can briefly outshine the combined light of every star in the observable universe. For a century, gravitational waves were just a beautiful mathematical consequence of Einstein's theory, seemingly impossible to detect. That all changed on September 14, 2015. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first historic direct detection. The signal, named GW150914, was a mere whisper in the data, a tiny chirp that lasted less than half a second. But that chirp told an epic story. It was the signature of two black holes, one about 36 times the mass of the Sun and the other 29, merging over 1.3 billion light-years away. The event was so massive that it shook the LIGO detectors by a distance 1,000th the width of a proton, a measurement of almost unimaginable precision. Since that first detection, the LIGO and Virgo observatories have heard the cosmic crashes of dozens of such mergers, each one a unique revelation. These observatories don't see in light, they listen for the vibrations of spacetime itself. Each gravitational wave signal is like a cosmic fingerprint, encoding the masses and spins of the black holes that created it. This has opened an entirely new window on the universe, a field known as gravitational wave astronomy. Before this, our knowledge of black holes came entirely from observing their effect on light, the way they distort the view of stars behind them or heat up gas in an accretion disk. Now we can hear them directly through the vibrations they create when they collide. This new sense is teaching us things we could never have learned by light alone. It has revealed a whole population of black holes of a size we didn't know were common. Stellar mass black holes far larger than any we'd found through X-ray studies. It has provided the most stringent tests yet of Einstein's general relativity, showing that its predictions hold true even in the most extreme gravitational environments imaginable. And with each new collision we detect, we are starting to build a census of how these dark objects live, pair up, and die in the vastness of space, giving us an entirely new narrative for the life cycle of the most mysterious objects in the universe. While the supermassive black holes at galactic centers command awe with their sheer scale, and stellar mass black holes offer a glimpse into the death throes of stars, the cosmic family of black holes is actually far more diverse. Astronomers classify these gravitational giants into three main categories based on their mass, and this classification reveals dramatically different stories of their birth and evolution in the cosmos. The most commonly known are stellar mass black holes, with a mass ranging from about 3 to 100 times that of our Sun. These are the ones we've discussed forming from the core collapse supernova of massive stars. When such a star exhausts its nuclear fuel, the outward pressure from fusion can no longer counteract the immense inward pull of gravity. The core collapses in a cataclysmic explosion, and if the remaining core is heavier than roughly 3 solar masses, no known force can stop it from compressing into a black hole. We've detected many of these through their interactions in binary star systems, where they pull gas from a companion star, heating it to millions of degrees and causing it to emit telltale X-rays that our telescopes can spot. Cygnus X1, one of the first strong black hole candidates discovered, is a stellar mass black hole about 21 times the mass of our Sun, locked in an orbital dance with a giant star. At the opposite end of the spectrum are the supermassive black holes, the million to billion solar mass behemoths that reign at the hearts of galaxies like our own Sagittarius A star. Their formation is a much greater puzzle than that of their stellar-sized cousins. They did not form from a single star. The universe hasn't existed long enough for a stellar mass black hole to consume enough matter to grow that large. Instead, they likely started from seeds in the early universe. One theory suggests these seeds were themselves substantial black holes, perhaps tens of thousands of solar masses, formed from the direct collapse of enormous clouds of primordial gas before the first stars even ignited. Another possibility is that they grew from the mergers of many smaller black holes and stars in incredibly dense early star clusters. Over billions of years, these seeds voraciously fed on surrounding gas and dust and merged with other growing black holes, eventually becoming the cosmic monsters we observe today. Between these two established classes lies the great mystery: intermediate mass black holes. Theorized to have masses between 100 and 100,000 suns, these objects are the missing link in the black hole family tree. Do stellar mass black holes slowly merge and grow into the supermassive ones we see? If so, there should be a population of mid-sized black holes on their way up. But finding them has proven incredibly difficult. They are too massive to be formed by a single star's collapse, yet they are not located in the bright, active centers of galaxies where we know to look for supermassive ones. They could be wandering the outskirts of galaxies or lurking within dense globular clusters. Their elusiveness comes from their nature. Without a consistent source of material to feed on, they wouldn't have a bright, hot accretion disk emitting copious X-rays. Without a companion star to steal from, they remain dark and silent. However, a few tantalizing clues have emerged. Astronomers studying the movements of stars in some globular clusters have noticed a gravitational tug that suggests a central object of a few thousand solar masses. Even more compelling evidence came from the detection of gravitational waves. In 2019, the LIGO and Virgo observatories detected a merger that created a final black hole of about 140 solar masses. The signal indicated that the two colliding objects were about 66 and 85 solar masses each, placing them firmly in the intermediate mass range and providing the strongest proof yet that these elusive middleweights do indeed exist, forging a crucial connection in our understanding of how black holes grow from stellar remnants to galactic kings. For decades, the reigning theory describing black holes was elegant in its stark simplicity. Known as the no-hair theorem, it proposed that these cosmic objects are, in a sense, the most boring things in the universe despite their terrifying power. The theorem's name is a playful metaphor. It suggests that black holes have no distinguishing features, no intricate details or complex structure, no hair. According to this idea, all you need to describe a black hole completely are just three numbers: its mass, its electric charge, and its spin. Imagine throwing an entire encyclopedia, a grand piano, and a box of assorted jewels into a black hole. The no-hair theorem claims that once it all crosses the event horizon, the black hole would simply gain more mass, its spin might change slightly, and that's it. Every single bit of information about what those objects were made of, their color, their composition, their history, is irretrievably lost. The black hole would be fundamentally identical to one that had swallowed only pure hydrogen gas of the same total mass. It's a concept that reduces the most complex objects to mere shadows defined by just three properties. This beautiful simplicity, however, creates a monumental conflict with another pillar of physics, quantum mechanics. A core principle of the quantum world is that information is never truly destroyed. It might be scrambled, encoded, or become incredibly difficult to read, but it can't simply vanish from existence. If you burn a book, the information in the words isn't gone. It's transformed into the specific arrangement of ash and smoke particles and the energy released. In principle, with an impossibly powerful computer, you could reverse the process and reconstruct the book. The no-hair theorem's suggestion that black holes destroy information outright created the infamous black hole information paradox, a problem that has troubled physicists for half a century. But what if black holes aren't bald after all? Recent groundbreaking research is challenging the classical view, proposing that black holes might indeed have a subtle form of quantum hair. This isn't hair you could see or touch. It's not a physical structure. Instead, it refers to incredibly faint imprints in the gravitational field surrounding the black hole, imprints that somehow preserve information about what fell inside. The idea suggests that as matter collapses into a black hole, it leaves a tiny, permanent fingerprint on the geometry of spacetime just outside the event horizon. This distortion is a quantum effect, a relic of the material's original properties, acting like a cosmic gravestone inscribed with information about what lies within. The implications of this discovery are profound. If verified, it could provide an elegant solution to the information paradox. The information wouldn't be lost inside the black hole, forever hidden from the universe. It would be preserved in this quantum hair, etched into the fabric of spacetime itself for those who know how to read it. This would mean that black holes don't violate the sacred rules of quantum mechanics after all. They aren't the ultimate shredders of information, but perhaps the most secure and complex libraries in the cosmos, storing data in a language we are only just beginning to decipher. This shift in understanding doesn't just tweak our models, it revolutionizes our entire conceptual framework for how gravity and quantum mechanics intertwine at the most extreme scales, suggesting that the universe has a fundamental way of remembering everything, even after it has seemingly vanished into the abyss. These bizarre theoretical objects push our understanding of gravity to its absolute breaking point, presenting a scenario even more unsettling than a standard black hole. The concept hinges on the very definition of a black hole itself, which is not the singularity but the event horizon that shrouds it. The singularity is the point of infinite density where our known laws of physics cease to function. The event horizon is the protective boundary that hides this breakdown from the rest of the universe. But what if that protective boundary could be torn away? This is the idea behind a naked singularity. According to the equations of general relativity, this could indeed happen under very specific and extreme conditions. The most plausible path involves a black hole spinning at the absolute maximum rate possible. As we discussed, a rotating black hole drags spacetime around it, and this spin also affects the shape and size of the event horizon. The faster it spins, the more oblate or flattened the event horizon becomes. The mathematics shows that if a black hole could be spun up to a critical threshold, the event horizon would pinch off at the poles and vanish entirely. What would be left is the raw, exposed singularity, a naked singularity, a point of infinite density sitting right out in the open universe for anyone to see, with no event horizon to act as a veil of censorship. This possibility sends a shiver through the foundations of physics because it creates what scientists call a pathology in spacetime. The fundamental principle of determinism, which allows us to predict the future state of the universe based on its current state, would completely break down. With a naked singularity, it becomes impossible to calculate what will happen next. The laws of physics as we know them cannot describe the conditions at the singularity, and if that singularity is not hidden, its unpredictable influence could propagate out into the universe. Cause and effect would break down. The ability to run the clock forward or backward would be lost. As renowned physicist Kip Thorne put it, a naked singularity would be a place where the universe is unpredictable, rendering the entire enterprise of science deeply problematic. Faced with this deeply unsettling prospect, physicist Roger Penrose proposed the cosmic censorship hypothesis. This is not a proven law, but a compelling conjecture that nature abhors such unpredictability. It suggests that the laws of physics conspire to prevent naked singularities from ever forming. Any gravitational collapse that appears headed toward creating one would, at the last moment, somehow form an event horizon, effectively censoring the singularity and protecting the rest of the universe from its lawless influence. In this view, every singularity must be modestly dressed in an event horizon, ensuring the universe remains orderly and predictable for those of us on the outside. While we have no definitive proof that cosmic censorship is a law of nature, the fact that we have never observed a naked singularity, despite looking for the exotic radiation it might emit, offers its strong support. It seems the universe might have its own built-in privacy settings, keeping its most dangerous secrets safely locked away. While the supermassive black holes at the centers of galaxies are often portrayed as dark, passive monsters, they can transform into the most luminous engines in the cosmos when they have a plentiful supply of fuel. This incredible transformation powers an object known as a quasar, short for quasi-stellar radio source. These are not mere stars. A single quasar can outshine the combined light of every one of the hundreds of billions of stars in its host galaxy, blazing with the power of 1 trillion suns from a region no larger than our solar system. This staggering energy doesn't come from nuclear fusion like in stars, but from the raw, violent conversion of gravitational energy into light and heat on a scale that is almost impossible to comprehend. The engine for this cosmic powerhouse is the black hole's accretion disk. Imagine a vast, chaotic whirlpool of gas, dust, and shredded stars, all spiraling inward at velocities approaching the speed of light. This isn't a smooth, orderly flow. It's a maelstrom of friction and colossal magnetic fields. As this material is pulled inexorably toward the event horizon, it doesn't fall straight in. Instead, it orbits the black hole, and different parts of the disk orbit at different speeds, causing the gas to grind against itself with unimaginable force. This intense friction, along with the twisting of powerful magnetic fields embedded within the plasma, heats the material to temperatures of millions of degrees. Matter this hot doesn't just glow, it radiates across the entire electromagnetic spectrum, from radio waves to incredibly energetic X-rays and gamma rays. The conversion of gravitational potential energy into thermal radiation in this process is phenomenally efficient. While nuclear fusion in a star converts less than 1% of mass into energy, the physics of an accretion disk can convert up to 40% of an object's mass into pure radiation as it falls inward. This is why a quasar, fed by a supermassive black hole, can produce such an unbelievable outpouring of light from a relatively small area. The light from these cosmic beacons does more than just illuminate their immediate surroundings. It acts as a brilliant lighthouse beam cutting across the universe. Quasars are so intensely luminous that we can detect them from the very edge of the observable universe, meaning we are seeing them as they were over 12 billion years ago, just a billion years after the Big Bang itself. This makes them invaluable tools for cosmologists. By studying the light from these distant quasars as it travels through billions of light years of space to reach us, astronomers can use it as a backlight. This light passes through clouds of primordial gas and the faint halos of intervening galaxies that would otherwise be far too dim to see. These cosmic clouds absorb specific wavelengths of the quasar's light, creating a unique barcode of dark lines in its spectrum. Each set of lines acts as a fingerprint, revealing the composition, temperature, and density of the invisible material it passed through. In this way, quasars are not just objects of study themselves. They are the ultimate flashlights, allowing us to map the large-scale structure of the universe and probe the nature of matter distributed between galaxies. The era of the most powerful quasars was the early universe, a more violent and chaotic time when galaxies were younger, gas was more plentiful, and black holes had an enormous amount of material to consume. As galaxies aged and this fuel was either consumed or blown away by the quasar's own tremendous radiation pressure, these brilliant engines gradually shut down. The quasar at the heart of a galaxy fades, leaving behind a quiet supermassive black hole like our own Sagittarius A star, a dormant giant remembering a more glorious and ferocious past. The discovery of quasars revolutionized our understanding of galactic evolution, showing that the darkest objects in the universe are also capable of generating its most brilliant light, and that the seeds of these cosmic monsters were already in place and feasting vigorously when the universe was in its infancy. While the supermassive black holes we've discussed are colossal and long-lived, the laws of physics allow for the existence of their exact opposites, tiny, fleeting micro-black holes. These theoretical objects would pack the immense gravitational punch of a black hole into a package smaller than an atom. The concept stretches our imagination, suggesting that black holes aren't just astronomical phenomena, but could also exist on a subatomic scale, born from the most extreme energies imaginable. Their potential formation is tied directly to Einstein's famous equation, E equals mc squared. This tells us that energy and mass are interchangeable. Under normal circumstances, to create a black hole with the mass of a star, you need the gravitational collapse of that entire star. But if you could focus a tremendous amount of pure energy into a vanishingly small point in space, that energy could theoretically warp spacetime enough to create a microscopic event horizon, forming a black hole without needing any stellar mass at all. The energy required is almost inconceivably high, far beyond anything we encounter in our everyday world or even in most cosmic events. This is where our most powerful machines come into play. Particle accelerators like the Large Hadron Collider at CERN are designed to smash fundamental particles together at velocities incredibly close to the speed of light. In these violent collisions, for a split second, the energy is concentrated into a point smaller than a proton. Some theories, particularly those involving extra dimensions of space, suggest that under these conditions, it might be possible to create a micro-black hole. The idea is that if our universe has more than the 3 spatial dimensions we experience, gravity could become much stronger at very small scales, lowering the energy threshold needed to warp spacetime and form a black hole. If such an event were to occur in a particle detector, what would we see? Contrary to popular science fiction fears, it would not begin sucking in the Earth. A micro-black hole created in this way would be incredibly ephemeral. It would have a mass far less than a speck of dust and would evaporate almost instantaneously due to the Hawking radiation process we discussed earlier. Its entire lifespan would be a minuscule fraction of a second. The telltale signature would not be a growing vortex, but a very specific burst of particles and radiation, the final flash of its explosive evaporation that detectors could potentially pick out from the chaos of other collision data. So far, despite extensive searching, no conclusive evidence for these micro-black holes has been found at the LHC, but the search itself pushes the boundaries of our knowledge about gravity and the fundamental structure of our universe. Beyond our particle accelerators, the early universe itself might have been a factory for these miniature marvels. In the first chaotic moments after the Big Bang, the entire cosmos was an incredibly dense, hot soup of energy. Fluctuations in this primordial density could have created regions where the pressure was so intense that micro-black holes formed spontaneously, like bubbles in a boiling pot. These hypothetical relics are known as primordial black holes. Unlike their lab-made cousins, some of these could have had a wider range of masses, from the microscopic scale all the way up to many times the mass of our Sun. Their survival to the present day would depend entirely on their initial mass. A very small one would have evaporated away by now in a flash of Hawking radiation, while a larger one could still be drifting silently through the galaxy today, utterly dark and nearly impossible to detect. The search for these primordial objects remains an active and fascinating area of astronomy, as they are candidates for the mysterious dark matter that shapes our cosmos. One of the most visually stunning and scientifically valuable effects a black hole has on its surroundings is its ability to act as a cosmic lens, dramatically warping the very path of light itself. This phenomenon, called gravitational lensing, is another incredible prediction of Einstein's general relativity made real. He proposed that massive objects don't just bend the paths of planets and stars, they bend the fabric of spacetime itself. And since light always follows the straightest possible path through this curved spacetime, its beam gets bent and distorted. A black hole, with its supremely concentrated mass, takes this effect to the extreme, creating a natural telescope of unparalleled power. Imagine a distant galaxy directly behind a black hole from our point of view. Instead of the black hole simply blocking the light, its gravity warps the space around it, creating a kind of lens. The light from the background galaxy is pulled and stretched as it travels around this gravitational well, forced to follow the curved geometry. Rather than a single point of light, we see a distinctive halo, a perfect circle of distorted light encircling the black hole. This beautiful structure is known as an Einstein ring, named for the physicist who first calculated this astounding possibility. If the alignment isn't perfect, we might see multiple smeared or mirrored images of the same background object, a cosmic illusion created by light rays taking different paths around the black hole before all arriving at our telescopes. This isn't just a theoretical curiosity. Astronomers actively use this effect as a powerful tool for discovery. By carefully analyzing the shape and brightness of these Einstein rings or multiple images, scientists can perform a kind of cosmic reverse engineering. The precise amount of distortion tells them exactly how much mass is causing the lensing effect and how that mass is distributed. This allows researchers to literally weigh the black hole and map the invisible halo of dark matter that surrounds it within its host galaxy. It's one of the most direct ways to study both the properties of the black hole itself and the mysterious dark matter that makes up the majority of the universe's mass, all through the subtle warping of starlight. The first direct visual evidence of this came from the Event Horizon Telescope collaboration's iconic image of the supermassive black hole at the heart of galaxy M87. The bright ring we saw was not the event horizon itself, but a perfect example of extreme gravitational lensing. That brilliant ring of light is the photon sphere, a region just outside the event horizon where gravity is so intense that photons of light are forced into a stable orbit. The light from the hot, swirling accretion disk behind the black hole is being bent and lensed around it, creating that unmistakable circular signature that confirmed our theories with breathtaking clarity. This ability to distort reality gives us a unique window into the most elusive components of the cosmos, turning the black hole's greatest trick, bending light to the point of capture, into one of astronomy's most valuable observational techniques. But even as we marvel at the power of quasars and gravitational lenses operating across billions of light years, some of the universe's most intriguing secrets are hiding much closer to home. In the vast expanse of our own galaxy, a silent hunter drifts through the darkness, and it is far nearer than most people would ever guess. The closest known black hole to Earth isn't a distant abstraction. It's a cosmic neighbor residing just 1,560 light-years away in the constellation Ophiuchus. To put that in perspective, if the entire Milky Way galaxy were the size of the Earth, this black hole would be a mere 15 miles away. This discovery fundamentally changes our perception of the solar system's place in the galaxy, revealing that we are living in a stellar community that includes the most enigmatic objects in the universe. This nearby black hole, named Gaia BH1, was not found by seeing the void it creates or the X-rays from a hot accretion disk. Instead, it was discovered by watching the subtle, telltale dance of a star that should not be dancing alone. Astronomers working with the Gaia Space Observatory noticed a sun-like star moving through space with a distinct wobble, as if it were gravitationally tethered to an unseen companion. By meticulously tracking the star's orbit, its velocity, and the slight tug on it, they could calculate the mass of whatever was pulling on it. The math revealed an invisible object with a mass roughly 10 times that of our Sun. Given that the most massive neutron stars can only be about 2 to 3 solar masses, the only possible explanation for this massive dark companion was a black hole. This method of detection, inferring a presence through its gravitational influence on a visible object, is a classic technique in astronomy, but Gaia BH1 presented a puzzle. The system is unusual because it's a quiet black hole. It's not actively feeding on its stellar companion, which means it isn't surrounded by the superheated disk of gas that would make it glow in X-rays and give it away. This makes Gaia BH1 a member of a new and elusive class, dormant stellar mass black holes. Its discovery suggests that our previous census of black holes was heavily biased. For decades, we primarily found them in loud, bright X-ray binary systems where they were actively stripping material from a partner star. But if this quiet, dormant black hole is so close, it implies that there must be a vast, hidden population of them scattered throughout the galaxy, going unnoticed because they have nothing to feed on. Statistically, there could be tens or even hundreds of millions of stellar mass black holes in the Milky Way, with many thousands residing much closer than Gaia BH1, silently weaving their way through the darkness between the stars. This changes our understanding of the galaxy's ecology. These dormant black holes are the ghosts of massive stars that lived fast and died young in supernova explosions. Their quiet presence means they could be drifting through any region of the galaxy, including our own cosmic backyard, completely invisible to our telescopes unless they just happen to pass between us and a distant star, causing a brief gravitational lensing event, or unless they have a companion star whose motion they disturb. The idea that our solar system might have had a close encounter with a black hole in its distant past is no longer the stuff of far-fetched speculation. It's a genuine possibility within the dynamic history of our galaxy. The discovery of Gaia BH1 is a powerful reminder that the universe's greatest mysteries aren't always in the most distant reaches of space. Sometimes they are hiding in plain sight, or rather in dark silence right next door. While the event horizon marks the point of no return, a black hole's influence often extends far beyond this dark boundary in the most spectacular fashion. Some of the most energetic black holes don't just pull matter in, they also fire out colossal, narrow beams of radiation and particles at nearly the speed of light. These structures, known as relativistic jets, can stretch for thousands or even millions of light years, punching far out into intergalactic space and becoming some of the largest single structures in the entire observable universe. The formation of these cosmic particle accelerators is a complex ballet of physics requiring a specific set of conditions. It begins with the accretion disk, that superheated whirlpool of gas and dust spiraling toward the event horizon. As this ionized plasma swirls inward at incredible speeds, it generates immensely powerful magnetic fields that become twisted and wound up by the black hole's own rotation like a cosmic dynamo. Not all of this infalling material actually crosses the event horizon. Some of it gets caught in these intense magnetic fields and is funneled away from the disk along the black hole's spin axis, the path of least resistance. This material is then launched outward from the poles at velocities so high that they are a significant fraction of light speed, focused into two opposing, incredibly narrow and precise beams. The energy to power this phenomenal eruption comes from two main sources: the black hole's immense gravitational pull and its own rotational energy. The gravitational energy of the infalling matter is converted into the kinetic energy of the jet. In the case of a rapidly spinning black hole, the process known as the Blandford-Zeenagic mechanism allows the black hole to directly transfer its own rotational energy to the jet, using the magnetic fields as a kind of cosmic transmission. This is why the most powerful and persistent jets are often associated with the supermassive black holes at the centers of active galaxies, where there is a vast and steady supply of material to feed both the accretion disk and this incredible engine. The impact of these jets on their surrounding environment is profound and paradoxical. On one hand, they are agents of incredible destruction. A jet plowing through a galaxy is like a cosmic blowtorch. The intense radiation and high-energy particles within the jet can heat and disperse the vast clouds of cold gas that are the raw material for new star formation, effectively sterilizing entire regions of a galaxy and quenching the birth of new stars. This is a key part of the feedback process that allows a supermassive black hole to regulate the growth of its own host galaxy. Yet, in a fascinating twist, these jets can also be catalysts for creation. When a jet slams into a particularly dense cloud of interstellar gas, it doesn't just blow it apart. It can also trigger shock waves that compress the gas, overwhelming the cloud's internal pressure and gravity and causing it to collapse. In this way, the very same force that prevents star formation in one area can actually initiate it in another, sculpting the galaxy's structure in complex ways. The jet from the supermassive black hole in the galaxy M87, which was famously imaged by the Event Horizon Telescope, is a perfect example of this dual nature. This jet stretches for 5,000 light-years, a visible testament to the black hole's power, and its interaction with the surrounding medium has undoubtedly played a major role in shaping the evolution of its galactic home for billions of years. For all their terrifying power, black holes are ultimately invisible, which makes the task of finding them a brilliant exercise in cosmic detective work. Astronomers cannot see the darkness itself. Instead, they must look for the undeniable gravitational influence these objects exert on their surroundings. One of the most powerful and direct methods for this involves watching the graceful and sometimes frantic dance of stars. Just as you might deduce the presence of the wind by watching leaves swirl in an otherwise still courtyard, scientists can pinpoint a black hole by observing stars that seem to be orbiting absolutely nothing. The most famous example of this plays out in the very heart of our own galaxy. For decades, astronomers had strong suspicions that a supermassive black hole, Sagittarius A, resided at the galactic center. But suspicion turned to certainty through the patient, meticulous tracking of a group of stars known as the S cluster. These stars are engaged in a perilous gravitational ballet, whipping around an invisible point at speeds that defy imagination. One star in particular, known as S2, has been a key witness. Its orbit is incredibly tight and fast. It completes a full loop around the unseen center of mass in just 16 years, reaching velocities of over 3 million miles per hour at its closest approach. The only object with enough gravitational might to hold a star in such a frenzied, high-speed orbit is a supermassive black hole. By precisely mapping the oval-shaped path of S2, scientists could directly calculate the mass of the object tugging on it. The math is stunningly clear. About 4 million times the mass of our Sun is confined to a region of space smaller than our solar system. This observation provided the most compelling evidence that Sagittarius A is indeed the supermassive black hole we now know it to be. But the story doesn't end with simply confirming its existence and weighing it. The extreme environment around our galactic center has become the ultimate laboratory for testing Einstein's theory of general relativity. According to Newtonian gravity, a star orbiting a single massive object should trace the same elliptical path over and over again, like a closed loop. However, general relativity predicts something more complex. The immense gravity of the black hole warps spacetime so profoundly that it causes the star's entire orbit to slowly rotate around the black hole over time. The point of its closest approach, known as the periastron, doesn't stay fixed. It shifts with each completed orbit. This gradual swiveling of the orbital path is called Schwarzschild precession. After following S2 for nearly 30 years, watching it complete multiple orbits, astronomers were able to directly measure this effect. The star's orbit is indeed precessing, and the amount of that shift matches the predictions of general relativity with remarkable precision. It's a breathtaking validation of a century-old theory, observed in the most extreme gravitational field we can study. Every shift in S2's path is a direct message from the fabric of spacetime itself, telling us that Einstein was right. This method of discovery, watching the motion of stars, has now become a standard tool. It's how we found our closest black hole neighbor, Gaia BH1, and it remains one of the most powerful ways to unveil these dark giants, proving that even the most secretive objects in the cosmos cannot hide the gravitational waves they send rippling through the paths of the stars that surround them. But what if the solution to one of cosmology's greatest mysteries has been hiding in these very shadows? For decades, astronomers have known that most of the matter in the universe is invisible. We can see its gravitational effects, the way it holds galaxies together and bends light, but we cannot see it directly. This elusive substance is known as dark matter, and its true identity remains one of the biggest unsolved problems in physics. While many scientists have searched for new, exotic subatomic particles as the answer, a compelling and elegant hypothesis suggests the culprit might be far larger and far older. A vast population of primordial black holes left over from the universe's explosive birth. This idea proposes that in the first chaotic fraction of a second after the Big Bang, the cosmos was not perfectly smooth. Tiny, random fluctuations in density could have created pockets of space so incredibly dense that they collapsed directly into black holes under their own immense gravity. Unlike the stellar mass black holes formed from dying stars, these primordial black holes could have been born with a wide range of sizes, from smaller than a pebble to more massive than a star. This primordial population, formed before the first stars even ignited, could be drifting through the universe in vast numbers, completely dark and invisible, yet their collective gravity could account for the effects we attribute to dark matter. However, a compelling idea must survive the harsh scrutiny of observation, and astronomers have devised incredibly clever ways to hunt for these hypothetical objects. One of the most powerful methods involves a phenomenon we've already discussed: gravitational microlensing. If a primordial black hole were to pass directly between Earth and a distant star, its gravity would act as a lens, briefly focusing the star's light and causing it to appear to brighten for a short period. The duration of this brightening event is directly related to the mass of the lensing object. Large-scale surveys that monitor millions of stars have indeed found such microlensing events, but not nearly enough to suggest that all dark matter is made of black holes in certain mass ranges. These observations have effectively ruled out primordial black holes as the sole explanation for dark matter if they fall within a mass range from about 1/1,000,000th of a solar mass up to about 100 solar masses. But the story doesn't end there. The window is still open for both very small and very large primordial black holes. At the smallest end, black holes with masses similar to a large asteroid would have evaporated by now due to Hawking radiation, leaving a flash of gamma rays that we have not observed in the predicted numbers. At the highest end, black holes with thousands of solar masses could still be viable candidates, and their collisions might be precisely what gravitational wave observatories are beginning to detect. The merger that created the 140 solar mass black hole detected by LIGO and Virgo in 2019 is a prime example. The progenitor black holes were in a mass range that is difficult to explain through stellar evolution alone, making them excellent candidates for primordial black holes. As our gravitational wave detectors become more sensitive, they will essentially take a census of black hole mergers throughout the cosmos. If a significant population of black holes is found in this intermediate mass range, and especially if they are found merging in the empty voids between galaxies where there are no stars to form them, it would provide stunning evidence that at least a substantial portion of the universe's dark matter has been hiding in plain sight all along, not as unseen particles, but as ancient gravitation. Ghosts from the dawn of time. For centuries, black holes existed as theoretical ghosts in the cosmos, entities we could only infer through their violent effects on the space around them. We saw the stars whipping around an invisible point at our galactic center. We detected the X-rays from superheated gas and heard the space-time ripples from their collisions. But seeing the unseeable directly imaging the black hole itself remained the ultimate dream, a feat that seemed to belong to the distant future. That future arrived on April 10, 2019, when the Event Horizon Telescope collaboration unveiled an image that shook the scientific world and captivated the public, the first direct visual evidence of a black hole. This historic portrait features the supermassive black hole at the heart of the galaxy Messier 87, a behemoth weighing in at 6.5 billion times the mass of our Sun. The image shows a strikingly bright, fiery ring encircling a perfect dark shadow at the center. This is not the event horizon itself, but something even more profound, the black hole's shadow. The luminous ring is the result of extreme gravitational lensing, the light from the billion-degree accretion disk being bent and warped around the black hole. The central darkness is the shadow cast by the event horizon, a region from which no light can escape, silhouetted against the brilliant background of the swirling gas. It is a perfect visual confirmation of Einstein's theories, showing us the precise shape that intense gravity carves out of the fabric of light. Capturing this image was a Herculean effort that bordered on the impossible. The target black hole is 55 million light-years away. From that distance, imaging its event horizon is like trying to photograph a donut on the surface of the moon. No single telescope on Earth possesses the resolution required to see such an infinitesimally small object. The solution was to transform our entire planet into a virtual telescope. The Event Horizon Telescope is not one instrument, but a synchronized network of 8 radio observatories spanning the globe from the high deserts of Hawaii and Arizona to the frigid peaks of the Andes and the Spanish Sierra Nevada, and even to the South Pole. By using a technique called very long baseline interferometry, these widely dispersed telescopes could act as one giant dish, a virtual observatory the size of Earth itself. The amount of data collected was staggering. Each telescope gathered so much information that it couldn't be transmitted over the internet. It had to be physically shipped on hundreds of hard drives to central processing centers. The data analysis was a monumental task, requiring years of work by hundreds of scientists to carefully calibrate, combine, and process the signals to reconstruct the final image. This was not a simple snapshot. It was a painstakingly crafted portrait from the faint whispers of radio waves that had traveled for 55 million years to reach us. The result was worth the wait. That now iconic image of a fiery ring of light is more than just a pretty picture. It is a treasure trove of scientific discovery. Its symmetry confirmed that the black hole is likely spinning. Its size perfectly matched the predictions from Einstein's theory of general relativity for an object of that mass. It provided direct visual proof that black holes, these mythical monsters of physics, are real, and that our understanding of their nature, forged from abstract mathematics, is fundamentally correct. This first image opened a new era of observational astronomy, allowing us to not just hear the universe but to finally gaze directly into the heart of darkness. This powerful influence that black holes wield extends far beyond their immediate surroundings, governing the very evolution of the galaxies they call home. We often picture these cosmic giants as destructive forces, but their true role is far more nuanced, acting as both creators and destroyers in a grand billion-year feedback loop that sculpts the cosmos. This process of co-evolution means that the supermassive black hole at a galaxy's center and the galaxy itself grow together, their fates inextricably linked in a delicate gravitational dance. The primary mechanism for this control is the incredible energy output from the black hole's active phases. When a supermassive black hole is actively feeding, it doesn't just quietly consume matter. It announces its feast with a torrent of radiation and the powerful relativistic jets we discussed earlier. This outburst floods the surrounding galaxy with an immense amount of energy, which interacts with the most crucial ingredient for galactic growth, cold gas. Galaxies are filled with vast clouds of this cold molecular gas, the raw material from which new stars are born. For a galaxy to continue forming stars and growing, this gas must be able to cool down, condense, and collapse under its own gravity. This is where the black hole steps in as a cosmic regulator. The intense radiation and high-energy particles from the active galactic nucleus heat this reservoir of cold gas, preventing it from cooling and collapsing. Think of it like a pot of water on a stove. If you turn the heat up high enough, the water will evaporate before it can ever freeze. In a similar way, the black hole's energy input keeps the galactic gas hot and agitated, effectively putting a limit on how many new stars can form. In even more extreme cases, the black hole's jets can act like a cosmic pressure washer, physically pushing vast quantities of gas right out of the galaxy entirely. This process, called quenching, can halt star formation entirely, preventing the galaxy from growing any larger. This might sound purely destructive, but this feedback is essential for creating the universe we see today. Without this regulatory mechanism, galaxies would continue to form stars unchecked, consuming all their available gas in a relatively short cosmic time and burning out quickly. The largest, most massive galaxies would become even more enormous. Instead, the black hole's activity prevents runaway growth, explaining why we don't see galaxies much larger than those we observe. It's a self-regulating system. As the black hole feeds and grows, it eventually unleashes enough energy to blow away its own food supply, forcing itself into a dormant state. This cycle of feeding and feedback ensures that galaxies evolve at a measured pace, with periods of vigorous star formation followed by long, quiet eras of stability. The evidence for this profound relationship is etched across the cosmos. Astronomers find strong correlations between the mass of a galaxy's central black hole and the properties of the galaxy itself, particularly the mass of its central bulge of stars. This tight relationship suggests that the growth of the black hole and the growth of the galaxy are fundamentally intertwined, each regulating the other over billions of years. The black hole, born from the collapse of matter, ultimately commands the fate of its entire galactic empire, not through relentless consumption, but through the brilliant, energetic feedback that maintains a cosmic balance, ensuring the universe is filled with a diverse population of galaxies of all shapes and sizes, each with a silent, dark heart governing its long-term destiny. Yet even the supermassive black holes that command entire galaxies cannot grow without limits. There appears to be a cosmic ceiling, a theoretical maximum size that these gravitational giants can reach. While we've observed black holes with masses in the tens of billions of suns, physicists believe there is a fundamental upper boundary, estimated to be somewhere around 50 billion solar masses. Beyond this point, the very mechanisms that fuel a black hole's growth begin to work against it, preventing it from becoming any larger. This ultimate size limit is governed by the physics of its own feeding mechanism, the accretion disk. For a black hole to grow, it needs a steady, massive inflow of gas to spiral inward, but this process generates an enormous amount of radiation. The energy released by the infalling matter creates an outward pressure of light that pushes back against the incoming gas. For smaller black holes, the immense gravitational pull easily overcomes this radiation pressure, allowing them to continue feeding. But as a black hole approaches that 50 billion solar mass mark, the balance of power shifts. The radiation pouring out from its accretion disk becomes so incredibly intense that it effectively acts like a cosmic blowtorch, heating and dispersing the surrounding reservoir of gas before it can even fall in. The black hole's own brilliant feasting ends up blowing away its future food supply, putting a hard stop on its growth through accretion alone. It's a self-regulating feedback loop of the most extreme kind. Another potential growth method is through mergers with other supermassive black holes, but this too has its limits. In the dense environments of galaxy clusters, mergers are common, but they also tend to fling the resulting, larger black hole out of the galactic center through the recoil of gravitational waves. This ejects it into a region where there is far less gas to consume, effectively stranding it and halting its growth. So, whether through accretion or merger, nature itself seems to impose a final, formidable barrier. The largest black hole we have ever discovered, Ton 618, puts this theory to the test. This is a celestial monster of almost incomprehensible scale. Lurking over 10 billion light-years away, it holds the mass of 66 billion suns. Its accretion disk is a maelstrom of hot gas so vast that it outshines the entire galaxy that surrounds it, making Ton 618 one of the brightest single objects in the known universe, a quasar of staggering power. It is teetering right on the edge of that theoretical maximum size, a testament to the most extreme conditions of growth in the early cosmos. Its very existence challenges our models and asks us to consider if even larger black holes could have formed in the unique, gas-rich environments just after the Big Bang, before the universe expanded and thinned out. Studying behemoths like this helps us understand the ultimate laws governing the lives and deaths of the universe's most dominant objects. While the isolated black holes we often imagine drift through the sparse emptiness of space, a far more dramatic and chaotic existence awaits them within the bustling stellar metropolises known as globular clusters. These ancient, densely packed spheres of stars are cosmic battlegrounds where black holes don't just live. They evolve, compete, and can be dramatically recycled through a relentless cycle of mergers and acquisitions. In these environments, a black hole isn't necessarily a final destination for matter. It can become the seed for an even larger object, growing far more rapidly than its solitary cousins. The process begins with the unique dynamics of a globular cluster. These regions contain hundreds of thousands of stars crammed into a relatively small volume of space. When massive stars within the cluster reach the end of their lives and collapse into black holes, their high mass causes them to rapidly sink toward the center of the cluster through a process called dynamical friction. This creates a dense nucleus of black holes at the cluster's heart, a dark counterpart to the brilliant sphere of stars surrounding it. In this chaotic central region, close encounters and direct collisions are not just possible, they are inevitable. Black holes frequently pair up through gravitational interactions, forming tight binary systems. These binary black holes then act as gravitational slingshots, ejecting other stars and black holes from the cluster as they trade energy, further tightening their own orbit. This intricate dance eventually culminates in a merger, releasing a torrent of gravitational waves and creating a single, more massive black hole. But the story doesn't end there. This newly merged larger black hole is now an even more dominant gravitational force within the cluster. It can then go on to capture another black hole or pull in more gas, beginning the entire process anew. This is the essence of recycling. A black hole gains mass through a merger, uses that increased gravity to find a new partner, and merges again. In the dense environment of a cluster, this cycle can repeat multiple times, allowing a black hole to grow to a substantial size through a series of mergers rather than just slow accretion. It's a fundamentally different growth mechanism from a lone black hole passively drifting through the galactic void, waiting for a chance encounter with a gas cloud. This relentless recycling has a direct and profound impact on the signals we detect with gravitational wave observatories like LIGO and Virgo. The black hole mergers originating from these dense environments often have very distinctive signatures. Because the pairing is driven by dynamic encounters rather than the evolution of a binary star system, the spins of the two black holes are typically misaligned and random, unlike the more aligned spins often seen in isolated binary systems. Furthermore, the repeated merger cycle can produce black holes in a specific mass range, the so-called upper mass gap between roughly 50 and 120 solar masses. This is a mass range where stellar evolution theory suggests it's difficult to form black holes directly from a single collapsing star, making a recycled origin a compelling explanation for their existence. When we detect a gravitational wave signal from a merger with random spins and a total mass in this gap, it's a strong hint that we're listening to the aftermath of a dramatic encounter in a dense stellar cluster, the latest chapter in a recycled black hole's violent history. But the violent dance of black hole mergers has a dramatic and often overlooked consequence. It can fling the resulting object out of its galactic home entirely. While we often picture these cosmic giants firmly anchored at the centers of galaxies, a significant population is actually drifting through the immense, empty voids of intergalactic space. These are the rogue black holes, solitary hunters cast out from their birthplaces and now wandering the cosmic wilderness, utterly invisible unless they happen to cross paths with a source of gas or an unlucky star. This ejection process is a direct result of the incredible physics of a black hole merger. When two black holes spiral together and finally become one, the event is not perfectly symmetrical. The emission of gravitational waves carries away momentum, and if this energy is ejected more strongly in one direction, it can rocket the newly merged black hole backward at tremendous speed, like the recoil from a cannon. This kick velocity can be astonishingly high, easily exceeding the escape velocity of even a large galaxy. In one swift, violent moment, the black hole is hurled out of its galactic core, sent on a one-way trip into the vast darkness between galaxies. These kicks are most powerful when the spins of the two merging black holes are misaligned with their orbital motion, a common occurrence in the chaotic environments of dense star clusters or during galactic collisions. Detecting these dark wanderers is one of astronomy's greatest challenges, as they give off no light of their own. Their presence is revealed only by their gravitational influence or by rare moments of activity. One method is gravitational microlensing. If a rogue black hole passes directly between Earth and a distant star, its gravity will briefly bend and focus the star's light, causing the star to appear to brighten for a period of days or weeks. The specific signature of this brightening can tell astronomers the mass of the invisible lens, confirming it as a black hole. Another telltale sign is a lone, flickering X-ray source moving rapidly through intergalactic space. This would indicate a wandering black hole that has managed to capture a wisp of gas or a small star during its travels, briefly igniting a tiny, hot accretion disk that betrays its position before it fades back into darkness as the fuel is consumed. The existence of these nomads reveals a much more dynamic and chaotic history for galaxies than we once thought. Every rogue black hole is a fossil record of a past merger, a silent witness to a violent event that reshaped its home galaxy. Their population tells a story of how galaxies grow by consuming others, with each major collision potentially ejecting the central black holes of the smaller merged galaxies. Some estimates suggest there could be thousands of these stellar mass exiles drifting through the halo of our own Milky Way and countless more, both stellar and supermassive, roaming the incomprehensible voids between galaxy clusters. They are the ghosts of cosmic battles fought long ago, forever wandering the endless night, reminding us that even the universe's most powerful objects are not immune to being cast adrift. But for all their immense gravitational power, black holes are not the cold, dead objects they were once thought to be. In a stunning revelation that connects the very large to the very small, we now understand that black holes have a temperature. This isn't a temperature in the everyday sense, like the heat from a fire. You couldn't take its temperature with a thermometer. It's a quantum mechanical temperature, a direct consequence of the ghostly process of Hawking radiation occurring just outside the event horizon. This temperature is determined by a beautifully simple yet profound relationship. The more massive the black hole, the colder it is. The temperature is inversely proportional to its mass. This means a supermassive black hole like Sagittarius, a star with millions of solar masses, has an incredibly low Hawking temperature, a tiny fraction of a degree above absolute zero. It's absorbing far more energy from the cosmic microwave background, the afterglow of the Big Bang that fills all of space, than it emits, so it continues to grow. This relationship completely flips for the smallest black holes. Remember those theoretical micro-black holes? For one of these, with a mass much smaller than a mountain, the temperature soars to astonishing heights. A black hole with the mass of an asteroid would be emitting Hawking radiation at a rate that makes its temperature climb into the millions of degrees. As it loses mass, it gets hotter and radiates energy away even faster, leading to a runaway process that ends in a spectacular final burst of gamma rays, a flash of light signaling its complete evaporation. This inverse connection between mass and temperature is one of the most elegant and unexpected links in all of physics, directly tying the behavior of gravity, described by general relativity, to the laws of thermodynamics, the science of heat and energy. A black hole isn't just a gravitational trap, it's a thermodynamic object with entropy, a measure of its internal disorder, that is also tied directly to the surface area of its event horizon. This deep connection suggests that the information about everything that has ever fallen in might somehow be encoded on this two-dimensional surface, a holographic representation of the three-dimensional volume within, a tantalizing clue in the quest to unify gravity with quantum mechanics. And in the most spectacular cosmic alchemy, black holes play a crucial role in forging the very elements that make up our world, including the precious gold in our jewelry and the uranium that powers our reactors. This incredible process doesn't happen within the black hole itself, but is sparked by the most violent events they help create, the collisions of ultra-dense neutron stars. When two neutron stars in a binary system finally spiral together and merge, an event often detected by its ripples in spacetime, the cataclysm creates the perfect conditions for the rapid neutron capture process, or the R process. In the energetic debris ejected from such a merger, a flood of free neutrons is absorbed by atomic nuclei at an astonishing rate, building them up into the heaviest elements in the periodic table in a matter of seconds. The signature of this cosmic forge is a brilliant flash of light known as a kilonova. Following the gravitational wave signal of a neutron star merger, telescopes swivel to capture the aftermath, witnessing a transient glow that is distinctly different from a supernova. The light from a kilonova is initially incredibly blue, dominated by the radioactive decay of heavy elements like cesium and tellurium, but it rapidly changes to a deep crimson red as even heavier elements like gold, platinum, and uranium take over the decay process. The first confirmed observation of this, accompanying the gravitational wave event GW 170817, was a landmark moment. Spectroscopic analysis of that red glow provided the direct, smoking gun evidence that these mergers are indeed factories for the universe's heaviest elements. While the merger itself is between neutron stars, black holes are deeply entwined in this story. Many of these systems might involve a black hole and a neutron star pair, with the black hole's immense gravity shredding its dense companion and drawing out a long tidal tail of neutron-rich material perfect for the R process. Furthermore, the very binary systems that lead to these mergers are often created in environments shaped by previous black hole interactions in dense star clusters. The gold ring on your finger or the platinum in a catalytic converter didn't come from the heart of a dying star. It was quite likely born in the spectacular fireball of a neutron star collision, a fleeting event made possible by the relentless gravitational dynamics that black holes help govern, making them silent partners in the creation of the complex chemistry that defines our planet. Ourselves, but to truly test the limits of physics, we must journey beyond the event horizon and confront one of the most bizarre and mathematically fraught regions in all of theoretical cosmology. For a rotating black hole, the event horizon is not the final boundary. It is merely the gateway to a realm where the very predictability of the universe begins to unravel. This inner domain contains a second theoretical boundary known as the Cauchy horizon or the inner horizon. It is here, deep within the black hole's structure, that the equations of general relativity suggest time itself could become unshackled, opening the door to paradoxes that defy our fundamental understanding of cause and effect. The existence of this inner horizon is a direct consequence of a black hole's spin. A rotating black hole, described by the Kerr solution to Einstein's equations, has a more complex internal anatomy than its non-spinning counterpart. Once you cross the outer event horizon, you are not immediately crushed. Instead, you enter a region called the ergosphere, where you are forced to move with the rotation of the black hole. Pushing further inward, you would eventually encounter the Cauchy horizon. This boundary is not a point of no return for matter. You could, in principle, cross it. But it is a point of no return for physics as we know it. The Cauchy horizon is where predictability, the fundamental principle that allows us to use the current state of the universe to calculate its future state, completely and utterly breaks down. Beyond this inner horizon, the equations of general relativity suggest that the future is no longer determined by the past. The path of spacetime itself becomes undefined. This mathematical oddity opens up staggering possibilities, none more famous than the potential for closed time-like curves. These are theoretical paths through spacetime that loop back on themselves, allowing an object to return to its own past. In this bizarre inner sanctum, the relentless forward arrow of time could become a circle, making time travel a mathematical possibility within the black hole's core. You could, in theory, encounter yourself from the future or become your own ancestor, creating paradoxes that violate the most basic tenets of causality. Naturally, physicists view this prospect with deep skepticism. A universe that allows such paradoxes is a universe where the consistent laws of physics cannot hold. This is known as the strong cosmic censorship hypothesis, a conjecture that suggests nature must abhor such unpredictability and that some mechanism, likely involving quantum gravity, must step in to protect the orderly nature of causality. The inner horizon might not be a stable boundary at all, but a place of immense quantum instability. The leading theory is that anything crossing the Cauchy horizon would be met with an infinite wall of energy, an effect called mass inflation. As an observer approaches, even the faintest ripple of radiation falling into the black hole from the outside universe would be focused and blue shifted to infinite energy at this inner boundary. This would likely destroy the inner horizon, replacing the paradoxical core with a true, space-like singularity long before any time traveler could ever reach it. In this view, the laws of quantum mechanics and general relativity conspire to act as a cosmic censor, erecting a firewall of energy to prevent the breakdown of physics and preserve a universe where cause always precedes effect. Beyond their awe-inspiring power and mysterious nature, black holes serve a profoundly practical purpose for science. They are the universe's most extreme natural laboratories. These gravitational giants create conditions so intense that they allow us to test the laws of physics in ways no Earth-bound experiment ever could. They push our theories to the breaking point, forcing us to confront the fundamental nature of reality itself. From the immense scales of general relativity down to the fuzzy, probabilistic world of quantum mechanics. The environment around a black hole is a unique arena where these two great pillars of modern physics are forced to meet, and they don't always get along. General relativity, which describes gravity as the curvature of spacetime, works flawlessly on large scales. It perfectly predicts the orbits of stars like S2 around Sagittarius A star and the gravitational lensing we observe. But it completely breaks down at the singularity, a point of infinite density where its equations simply spit out nonsense. quantum mechanics, which governs the behavior of atoms and particles, is brilliantly successful in its own domain but has no description for gravity. The event horizon is the battleground where these two theories clash, and by studying phenomena like Hawking radiation, a quantum effect that occurs at the gravitational boundary of the event horizon, scientists get their best clues for how to forge a new, unified theory of quantum gravity. This laboratory also allows for incredibly precise tests of general relativity itself. The precession of a star's orbit near a black hole is one such test, but there are even more exotic possibilities. Some theories propose that the fundamental constants of nature, like the speed of light or the fine structure constant, might not be perfectly constant across the universe. The insane gravitational fields near a black hole could potentially magnify any tiny variations in these constants. By meticulously studying the light from the accretion disk or from stars orbiting very close to the event horizon, astronomers can hunt for any slight deviations from the expected atomic spectra, which would signal a change in physics itself under extreme duress. Furthermore, the sheer density and powerful magnetic fields present in these regions make them ideal hunting grounds for particles that have so far eluded our detection. Theorists suggest that black holes could be factories for, or magnifiers of, proposed particles-like actions. These are hypothetical, ultralight particles that are leading candidates for cold dark matter. In the intense conditions around a black hole, actions could be produced in large numbers and even, through a process called superradiance, extract energy and angular momentum from a spinning black hole, creating a cloud of particles around it that would emit a distinct signature of radio waves. Similarly, other proposed particles like dark photons or weakly interacting massive particles could reveal their presence through subtle effects on the behavior of matter falling into a black hole or the characteristics of the Hawking radiation it emits. By turning our telescopes toward these cosmic labs, we aren't just looking at black holes. We are conducting some of the most sensitive experiments imaginable in the search for the true, complete laws of the universe. Even the most ravenous cosmic feast can sometimes lead to a case of indigestion, and for a black hole, this results in a surprising cosmic belch. We often picture these gravitational giants as insatiable vacuum cleaners, but their feeding habits are far more complex and messy. When a star ventures too close to a black hole, it doesn't always get swallowed cleanly. It gets ripped apart in a spectacularly violent event known as a tidal disruption event. The black hole's immense gravity creates a tidal force so powerful that it stretches the star horizontally while compressing it vertically, pulling it apart into a long, thin stream of gas in a process called spaghettification. About half of this stellar debris is then flung out into space, while the other half forms a swirling, superheated accretion disk around the black hole, fueling a brilliant flare of light that can outshine an entire galaxy for months. But sometimes the story doesn't end there. Astronomers have observed something peculiar happening months or even years after the initial flash fades. Following the brilliant flare of a tidal disruption event, the light curve can show a second, unexpected brightening. It's as if the black hole, after its enormous meal, has let out a delayed cosmic burp. This isn't a belch of gas in the traditional sense, but a powerful outflow of material, a jet or a wind. That was launched after the initial feast. This delayed outflow indicates that the accretion process is not a simple, smooth flow of material into the abyss. Instead, it's a chaotic and unstable process full of fits and starts. The leading theory for this delayed reaction involves instabilities within the accretion disk itself. Imagine that initial stream of stellar gas swirling in to form a disk. This disk can become unstable, perhaps due to its own magnetic fields or the tremendous radiation pressure building up within it. Material might initially pile up in the outer regions of the disk, much like food getting stuck before finally moving through a digestive system. This accumulation creates a reservoir of gas that can't immediately fall inward. Then, after a significant delay, a sudden shift occurs, a magnetic flip, a thermal instability, or the reaching of a critical density that triggers this stored material to rapidly fall toward the black hole all at once. This sudden, massive influx of fuel can power the launch of a jet or a strong wind, creating that secondary burst of emission that we observe as the belch. This phenomenon is more than just a quirky bit of cosmic biology. It's a vital clue that challenges our simplified models of how black holes consume matter and regulate their growth. It shows that the accretion disk is not a steady, continuous whirlpool, but a dynamic and volatile structure that can store and release energy in unexpected ways. Each of these observed burps gives astrophysicists a new puzzle to solve, forcing them to refine their simulations to include these complex delays and outflows, helping us to better understand the intricate and often messy relationship between a black hole and its surrounding environment. Yet for all their terrifying power, the most problematic part of a black hole might be the very thing that defines it, the singularity. This point of infinite density, where all known laws of physics break down, has long been a source of deep frustration for theorists. It represents a fundamental failure of our understanding, a glaring signpost that general relativity is incomplete. But what if the singularity isn't real? What if it's merely a mathematical artifact that vanishes when we apply a more complete theory of quantum gravity? This leads us to one of the most mind-bending ideas in modern theoretical physics. Black holes might be able to exist without singularities at all. One of the most compelling alternatives is a hypothetical object known as a gravistar, short for gravitational vacuum star. Imagine a black hole, but instead of an event horizon hiding a disastrous point of infinite density, the gravistar has a surface. This surface isn't made of normal matter. It's a bizarre, ultra-thin shell composed of an exotic form of energy, similar to the dark energy that is causing the accelerated expansion of the universe. Inside this shell, the interior of the gravistar isn't empty space filled with a singularity, but a region of completely vacuumed-out negative pressure space-time. This core of dark energy would be incredibly dense, but it would have a finite density, avoiding the mathematical nonsense of a true singularity. From the outside, a gravistar would look almost identical to a black hole. It would have immense gravity, bending light and trapping it into orbits, creating the appearance of an event horizon and a shadow. Yet, because it lacks a true point of no return and a singularity, it potentially sidesteps many of the thorniest problems, like the information paradox, entirely. Another radical reconception comes from the field of loop quantum gravity, which attempts to quantize spacetime itself. In this theory, the fabric of the universe isn't smooth and continuous all the way down. It's woven from tiny, discrete loops. This has a profound effect on the extreme conditions inside a black hole. Rather than matter collapsing into an infinitely dense point, the loop quantum gravity model suggests that at a very small scale, a repulsive force generated by the quantum geometry of spacetime itself kicks in. This force becomes stronger than gravity, preventing a complete collapse. Instead of forming a singularity, the collapsing matter would rebound like a cosmic bounce. The result wouldn't be a black hole as we classically imagine it, but a bridge to another region of spacetime, a concept that aligns with the idea of a wormhole. In this scenario, the black hole's interior contains not a deadly end point, but a tunnel to another universe or another time, a concept that transforms them from ultimate endpoints into potential gateways. These ideas aren't just wild speculation. They are serious mathematical constructs designed to resolve the deep conflicts between gravity and quantum mechanics. The beauty of these models is that, for an outside observer, they are nearly indistinguishable from a classic black hole. They predict the same gravitational lensing effects, the same accretion disk physics, and the same shadow that was so brilliantly captured by the Event Horizon Telescope. The differences are hidden deep within, in a realm we cannot yet directly probe. The key to testing them may lie in the most subtle of signatures, perhaps in the precise way they vibrate and ring like a bell after a collision, or in the specific pattern of Hawking radiation they might emit. By searching for these tiny deviations from Einstein's predictions in gravitational wave signals and future black hole images, physicists hope to catch a glimpse of what truly lies at the heart of darkness, potentially discovering that the universe has an even more bizarre and elegant structure than we ever dreamed. But for all the terrifying finality of the event horizon, some of the most captivating ideas in theoretical physics suggest that a black hole might not be an ending at all, but a beginning, a gateway to another reality. This speculative concept transforms the ultimate cosmic trap into a potential portal, connecting our universe to another through a theoretical tunnel in space-time known as a wormhole. The mathematics of Einstein's general relativity doesn't forbid such structures. In fact, it provides a possible blueprint for them. One particular solution to his equations, known as the Einstein-Rosen bridge, describes a wormhole as a shortcut through the fabric of the cosmos, a tunnel linking two distant points in space or even two entirely different universes. The intriguing connection to black holes emerges from this math. One end of this hypothetical tunnel could behave just like a black hole, a one-way entrance where matter and light are pulled in. But the other end would be its exact opposite, a white hole. Imagine a black hole in reverse, a region of space-time from which energy and matter can only pour out, but nothing can ever enter. If such an object existed, it would violently expel everything it contained into another region of space or another universe entirely. In this wild scenario, a black hole in our cosmos would not be a final destination but a cosmic transfer station, sucking material in here and spewing it out somewhere else, making it a one-way ticket to an unknown destination. However, there's a colossal catch that keeps this idea firmly in the realm of theoretical speculation. For such a wormhole to be stable enough and large enough for anything to actually pass through it, it would require a truly bizarre substance known as exotic matter. This isn't just unusual material, it's matter that possesses negative energy or negative mass, something that has never been observed in nature. Normal matter with positive mass creates gravity that attracts and warps space-time in a way that would cause any wormhole to collapse instantaneously into a singularity. Exotic matter, with its negative energy density, would theoretically generate a kind of anti-gravity, propping the throat of the wormhole open and preventing it from pinching shut. Without this mythical material, any wormhole would snap closed the moment it formed, making traversal utterly impossible. This profound requirement for unproven physics is why the idea remains a fascinating thought experiment rather than a working theory. No white hole has ever been observed, and the existence of exotic matter is purely hypothetical. The universe, as far as we can tell, seems to favor the existence of black holes as endpoints, not as passages. Yet, the mathematical possibility continues to inspire physicists and captivate our imagination, serving as a powerful reminder that our understanding of the cosmos is still evolving. It challenges us to consider that the most extreme objects in the universe might hold even deeper secrets, not just about how our universe ends, but about how a multiverse of realities might potentially connect. While the incredible energies of black hole mergers and the brilliant flares of quasars define the universe in its vibrant youth and middle age, these gravitational giants also hold the key to understanding its final, quiet end. To grasp the ultimate fate of the cosmos, we must fast forward to a time so far in the future that the universe becomes an almost unrecognizable, cold and dark expanse. In this unimaginably distant era, the last significant structures remaining may not be galaxies or stars, but the very black holes we see as cosmic destroyers today. Their final evaporation, a process set in motion by the faint whisper of Hawking radiation, could mark one of the last meaningful events before the universe settles into a permanent state of equilibrium known as the heat death. This journey to the end of time begins with the gradual dimming of the universe. Over trillions upon trillions of years, all the fuel for star formation will eventually be exhausted. Galaxies will have burned through their reservoirs of gas, and the last generation of stars will fade away, leaving behind a cosmic graveyard of stellar remnants, cold white dwarfs, neutron stars, and black holes. These objects will drift further and further apart as the universe continues its accelerated expansion, becoming isolated islands in a sea of ever-cooling emptiness. In this frozen, dark epoch, the only sources of light will be the occasional flash of two brown dwarfs colliding or the faint glow from the radioactive decay of elements within dead stars. The temperature of the entire cosmos will creep ever closer to absolute zero. Yet, even in this profound darkness, black holes will persist. Their immense gravity makes them incredibly durable, outlasting all other structures. A stellar mass black hole will continue to exist for an almost incomprehensible duration, but due to Hawking radiation, they are not truly eternal. As we discussed, this quantum process causes them to very slowly lose mass, and this evaporation accelerates as they get smaller. For a black hole with the mass of our Sun, the timescale for complete evaporation is an astronomically long number, a 1 followed by 67 zeros years. That is far, far longer than the current age of the universe, but given an infinite amount of time, even these cosmic titans will eventually succumb. The final moments of a black hole's life are not a quiet fade-out but a spectacular, violent crescendo. As it shrinks, its temperature skyrockets. In its last second of existence, a black hole with a mass of 1,000,000 tons would release the energy equivalent of a 1 megaton nuclear bomb. The final evaporation would be a tremendous burst of high-energy gamma rays and particles, a brilliant flash in the otherwise endless night, signaling the complete conversion of the black hole's mass into radiation. This energy will then slowly redshift and dissipate into the vast, cold emptiness, contributing to the universe's final, uniform state of maximum entropy. This process ties the life cycle of a black hole directly to the grandest scale of cosmic evolution. The largest supermassive black holes, with billions of solar masses, will be the last to evaporate, their lifetimes stretching into numbers so vast they have no practical meaning. Their eventual disappearance may very well be the last definitive event of structure and change in the entire history of the universe. After the last black hole has radiated away, the cosmos will enter its final perpetual state, a near-perfect vacuum populated only by a sparse, dilute sea of fundamental particles and low-energy radiation, all at a uniform, frigid temperature. There will be no more energy gradients, no more structures, and no more processes capable of doing any meaningful work. This is the heat death, the ultimate triumph of entropy, where time itself may become meaningless because nothing ever changes. In this profound context, black holes are not just endpoints, they are the universe's ultimate timekeepers. Their formation in the violent deaths of massive stars helped seed and shape galaxies. Their mergers shook the fabric of space-time, and their incredibly slow evaporation through Hawking radiation provides a clock that ticks across near eternity, connecting the fiery beginnings of the cosmos with its cold, quiet, and final end. They are a constant throughout the entire narrative of the universe, from the first seconds after the Big Bang to the very last conceivable event trillions of years in the future, making them one of the most significant and enduring characters in the greatest story ever told. So as we reach the end of our journey through these 30 astonishing revelations, it's clear that our perspective on black holes has undergone a complete transformation. We started by seeing them as the universe's ultimate monsters, cosmic vacuum cleaners lurking in the dark, but we now understand they are so much more than that. They are fundamental architects of the cosmos, playing a critical role in the birth of galaxies, the distribution of the elements that make up our world, and even the flow of time itself. From the faint whisper of Hawking radiation to the universe-shaking crash of a merger, their influence is woven into the very fabric of reality, acting as both creators and destroyers in a delicate billion-year dance that shapes everything we see. This new view invites a profound sense of wonder. The universe is far stranger and more interconnected than we ever could have imagined. The same forces that create a terrifying point of no return also forge the gold in a wedding ring. The same object that can tear a star apart also helps hold an entire galaxy together. The same gravitational trap that seemingly destroys information might actually preserve it on a quantum holographic surface. These aren't just cold, dead voids. They are dynamic, evolving entities with temperatures, life cycles, and a story that stretches from the first instant after the Big Bang to the very last moment of heat death trillions of years in the future. This journey of discovery is far from over. With every new gravitational wave detection, every deeper image from the Event Horizon Telescope, and every innovative theoretical breakthrough, we peel back another layer of the mystery. The greatest lesson these 30 facts teach us is to embrace the unknown, to stay curious, and to always look up at the night sky with a sense of awe for the incredible secrets it still holds. The cosmos is the grandest story ever told, and we are just beginning to learn how to read it. We would love to hear which of these facts reshaped your view of the universe the most. Was it the bending of time near the event horizon, the revelation that black holes can evaporate, or the incredible idea that they might be hiding the key to dark matter? Share your favorite cosmic insight in the comments below. Let's keep this conversation about the wonders of the universe going. Thank you for exploring these mysteries with us. Remember to like this video if it expanded your mind, and subscribe so you don't miss our next journey into the unknown. Until next time,